Welcome back to my introductory series on the fundamentals of the K40 laser systems. I would like to thank everybody that's provided comments and feedback. It's been great hearing from people, and I try to respond whenever possible. So please like, dislike, enter, comment, and subscribe. It all helps. For starters, I'd like to address a couple of comments and questions that were asked. One is where I'm at with my upgrades. The short answer is I'm still in the same spot I was before. Life has kind of gotten in the way. I haven't had much time to play around with my laser or do much work on it. I do have plans to do some upgrades in the near future. I will film anything that I do and post that as part of this channel. The other question I've gotten asked by a couple of people is where I got the laser protected glasses. And the eBay listing that I bought those off is no longer there. I also don't feel real comfortable providing a specific link to go buy these particular glasses. What I do recommend is that when you look for laser safety glasses, look for something specifically that is for the frequency range of 10,600 nanometers for that wavelength, and make sure that what you're looking at is not, like a $5 pair of safety glasses with a funny tint. A lot of laser safety glasses, especially on eBay and the cheaper sites, that's what they are. They're basically tinted, polycarbonate lenses. They're not true laser safety glasses. Perhaps in the future I might do an efficacy test in comparing different laser safety glasses and showing the effects. Now, there is another individual that has done a series of tests on laser safety glasses. They were not using CO2 lasers, they were using high-powered green lasers, but a test similar to that for the CO2 laser. But just remember, 10,600 nanometers is the wavelength of a CO2 laser, and that's what you're looking for. You'll find a lot of the laser safety glasses out there that are out there for 800 or 1200 nanometer, not designed specifically for USB, not specifically designed for CO2 lasers. And with that, we'll get into this fundamental series on the light path of the CO2 laser. Okay. Let's start off with what I define as the light path. It's a series of optical components that direct the infrared laser beam from the CO2 laser tube to the work surface. That includes mirrors, lenses, and the beam combiners. There's some non-optical components that support the light path, including mirror mounts, the print head bracket, and combiner mounts. Now, out of all these components, probably the single most important piece of the light path is the mirrors, outside of the actual laser tube itself. Without the mirrors, your laser's not getting anywhere near the workpiece. So the first thing we have to think about is, what is the mirror doing? It's reflecting that light, but the typical mirror that you see in your household is what's called a second surface mirror. So if you look at this diagram here, we have our light coming in, it hits the surface of the glass, it refracts a little bit, hits the second surface of the mirror, which has a silvered coating. Usually actually is a thin layer of high quality silver, and then it bounces off and then refracts again at the other side. So you get an angle of incidence is equal to angle of reflection and all of that, a little bit of refraction going on, but essentially the light comes in, goes out, same angle it came in. This won't work for a CO2 laser. The reason being is that glass is opaque to CO2. So is acrylic and other things. This is why you can cut acrylic with the laser. The light doesn't go through it. As far as infrared is concerned, that's as opaque as a piece of aluminum is to visible light. So that's why the laser can cut acrylic and things like that and etch the surface of glass. What we need is what's called a first surface mirror. And what you'll have is a glass or silicon substrate and typically a gold coating. Now, there are other types of mirrors that are a solid material, like they're solid copper or brass or something like that, and it's polished to a high finish. And we'll talk about those a little bit. Let's talk a little bit about the different types of materials that you can get for your mirrors. The cheapest, and I'll tend to go from the cheapest to the most expensive options, or try to stick to that order. You'll see them advertised on eBay and Amazon, and they'll say K9 mirrors. What are the K9? It sounds really great. But what it is it's glass. It's a glass substrate with a gold coating. The cheaper they are, the poorer that coating. So glass is nice and hard, makes a really hard, flat surface for them to work off of, but it does not handle thermal shock well. So if your mirrors are getting hot for some reason, which we'll discuss why that might be, you will find that you'll sacrifice your mirrors fairly regularly. The advantage is they're cheap. You can buy these mirrors for really cheap, use them for a while, throw them away. Another disadvantage is this gold. Gold is not a very hard metal. It does not stand up to scratches very well. So something we have to watch out for. The next up would be a silicon substrate. Same principle, except that instead of glass, it's using a silicon wafer back here. Silicon handles heat a lot better than glass, so it can take a little bit more of a beating. Same disadvantage with the gold coating, though. That gold coating is still not as hard as it could be, so you can easily scratch that surface and affect your mirror's functionality. One of the solid materials is copper, so you can get a copper plate, and essentially it's just a copper disc that has been polished to a high finish on the surface. Copper is harder than gold, so it stands up a little bit better. Not quite as reflective, so you'll lose a little bit of energy there, but it is definitely harder and definitely handles the thermal shock well because it is a piece of metal and it can absorb a lot of heat. It's not going to shatter. You get it hot enough, it will eventually melt, but a typical 40-watt laser is not going to be able to melt a piece of copper in any time. The next level up would be a molybdenum. Yeah, tongue twister. Molybdenum mirror. They have great thermal handling. Very hard surface. Molybdenum is added to steels to make it harder, more durable. You'll find it in tool steels. It's also not quite as reflective as gold, but highly polished, and it'll stand up to some beating. So if you're going to deal with a lot of scratching, might be something to consider. Invest in that little bit more expensive mirror. For special mention, I have seen a couple of things where people talk about using hard drive platters. Now, if you've ever taken a computer's hard drive apart, you'll find that platter is very highly polished. It's very reflective. I don't know how it would compare to a piece of gold, the gold plating on a K9 mirror or a silicon substrate mirror. But that hard drive platter, could be a nice cheap way to make a mirror. However, one thing to be aware of is that, although it has a metal base, has good thermal shock characteristics and stuff like that, you have to have tools to make these. You can't just go out and grab yourself a pair of tin snips and cut out an aluminum plate. You're going to need to have some precision tools to be able to do this. So it might be something that you could do if you've already owned those tools, but you're probably not going to save any money if you go out and have to buy yourself miniature lathe and tooling and all of that to turn these in, and then get a whole bunch of used hard drives. So very special mention for those. The second most important piece of your laser light path is the lens. The reason for this is the lens power effect. So a lens does not actually increase the power, but it focuses that power into a smaller area. So if we look at this as watts per unit squared, which would be watts divided by the pi times the radius squared of the dot that we're creating. If you look at the beam that's coming directly out of the laser, approximately 4 millimeters in diameter, a 40 watt laser power. So the diameter of that is, or the radius of that is 2, so we got pi times 2 squared. We have approximately 12.56 square millimeters of area. We divide that 40 watts by that 12.56 millimeters squared, and we get 3.18 watts per square millimeter. Now if we focus that beam down to 0.25 millimeters, now this is nowhere near as tight as it can actually be focused. as a rule of thumb, you can focus your beam down to the same diameter as the wavelength of the beam. So in this case, 10.6 micrometers, which would be 0.016 or 0.0106 millimeters. So, but if we look at a 0.25 millimeter focus beam and 40 watt power, we have 0.196 square millimeters divided by that, or 40 watts divided by that, we have approximately 204.08 watts per square millimeter. A substantial power increase, and this is why we need that lens to focus our beam, in addition to making the smaller dot for more precise images. Now, where that dot focuses is called the focal length. And you'll find that your lenses have different focal lengths depending on what you're doing. Very typical 50.8 millimeters or 2-inch focal length is very common. So if we look at that really closely, the focal length is the distance from the bottom of the mirror to the point where you have the smallest dot possible. This focal length is important. So a shorter focal length is going to have a much shorter depth of field as well, and that's an important aspect of your laser. So your depth of field is from where the beam is no more than 1.4 times the diameter of the smallest point. So if your smallest point is, say, 0.1, and that means that from where the beam gets to 0.14 to where it reaches 0.14 on the other side, that would be your depth of field. That's considered your cutting area. Shorter focal lengths tend to have a shorter depth of field, but also a sharper focus. Longer focal lengths have less of a focus, or a larger dot focus, but have a much longer depth of field. So if you're cutting thicker material, you may want a longer depth of field. Cutting thinner material, you want a shorter depth of field. Of course, the important part is having your work surface adjusted so that the focus point is at the right point, because having a 2.5-inch depth of field won't do you any good if your laser lens is 2 inches above your work surface. So something to keep in mind. Additionally, we have shapes of your lenses. So there's two major shapes that you'll run across. There's actually many more than this, but typically in the laser, Chinese lasers, you're going to find plano convex mirrors and positive meniscus mirrors. Plano convex just means it's got a plane on one side and a convex surface on the other. The convex surface is always your laser side. Your work side is the plane side, or the flat side. Now, plano convex mirrors are very simple to make, or lenses are very simple to make. Flat side, rounded side, relatively easy, which makes them the more common and a little bit less expensive option. And then you have the positive meniscus mirror, which has a convex side and a concave side. Now these tend to have a little bit better focus. And again, the laser side is your convex side. Your work side in this case is the concave side. And if you're putting your laser lens back in and you're not sure, with a plano convex mirror, if you look at that lens, and if the reflection in that lens is small, then that's your convex side. If you look at it and you see your reflection in that lens and it's basically a normal reflection, then that's your plane side. So again, plane side always goes towards your work surface. In addition to the shapes, we have different materials that you can get your lenses made out of. The most common is zinc selenide. It transmits visible light as well as CO2, so if you're using a beam combiner, you'll need to make sure that you're using a material that transmits that visible light that you're trying to bring down there. It also has the lowest absorption of the lens materials. This is a good thing, and probably the most common lens type that you're going to see. There is also gallium arsenide. It's a very high hardness material, very durable. It does not pass visible light, so if you're going to try and have a red laser targeting beam, you can't use gallium arsenide or gas lens. You have to use a zinc selenide. And the third material, and I've never actually seen it available for purchase, but in theory, is germanium. It's a poor material for higher wattages. It does not handle heat very well. Does not pass visible light. It's semiconductor material like gallium arsenide and silicon stuff. So, but it just doesn't handle the heat very well. Germanium will absorb too much heat and greatly weaken it and damage it very quickly. So you won't see this typically in a 40-watt laser realm. So when you're looking to buy lenses for your machine, you got to remember there's 3 critical dimensions and one that's going to be related to those dimensions. First is your focal length. How far away is your work surface from your laser? And if you don't have an adjustable deck, you need to make sure you get a focal length that matches your machine's deck height. Again, if you get a 2.5-inch focal length, that's great, but if your deck's only 2 inches away, your laser is going to be out of focus and you're never going to be able to get a good cut. The second is the diameter, and the third is the thickness. Now both of those are just physical dimensions. Is it a 2 millimeter thick lens or a 3 millimeter thick lens? Is it an 18 millimeter diameter lens or 20 millimeter diameter lens? These materials are not something that you can rework later. If you order the wrong lens, your only option is to order the right one. You have a 20 millimeter diameter lens, you're not going to be able to trim it down and make it fit in an 18 millimeter lens holder. And the fourth dimension that is dependent on the first is your depth of field. So again, if you have a long focal length, you're going to have a longer depth of field. You're going to be cutting thicker materials. You may want that longer depth of field for to be able to pass through those materials and have a cleaner, squarer cut all the way through and stay in focus a little bit longer. So the next piece that could be in your light path, which is not critical to the light path, nor is it probably installed on your base system, is a beam combiner. And the purpose of the beam combiner is to allow you to transmit a visible laser along the same path as your infrared laser. You can use this for targeting and identifying starting points and so forth. And what it does is it sits at a 45-degree angle to your beam path and allows you to shoot the visible layer. It comes in the side, hits this, which is reflective to visible light but transparent to the infrared, and bounces into the beam path. The infrared light would just pass directly through it with minimal power loss. So there's a few different materials that you'll see used for the beam combiners. Zinc selenide, just like the lenses, is used because again it's transparent to the infrared, this clear piece of glass, and is somewhat reflective to the visible laser. Zinc sulfide is another material, as well as germanium. So again, the critical dimensions on these will be your thickness, your diameter, and your angle of incidence, which should be 45 degrees. It should just always be a 45-degree angle to your beam path, but make sure you get the right material and dimensions, so forth. So the final step, or final thing we're going to discuss here, is care of this optical path. So for starters, we'll look at the care of your mirrors. Cleaning your mirrors. Why should you clean your mirror? What's so important about having the mirror cleaned? And it's not so you can look pretty in it. It's quite simply because anytime any amount of energy that is not reflected, something has to happen to it. If it's not reflected, then it's converted into heat, which is absorbed into your mirror. And if you have a substrate that can't handle it, you'll end up with a situation like this. This is a picture of a mirror that came off of my machine shortly after I got it. I had cut some material, didn't realize that I had got some residue on this mirror, and shortly thereafter the beam shattered the mirror and it obviously stopped working. So, anytime anything's dirty, it's going to absorb energy rather than transmit it. That means that's energy not getting to your material for cutting. It's also energy that is being converted into heat and having to be absorbed by your machine. So how do you clean these mirrors? First of all, wear gloves. Nitrile gloves or cotton gloves, something to keep your the oils and acids from your fingers from getting on these mirrors. Again, that gold is very thin, very soft, and can be destroyed very easily. So throw on some gloves, isopropyl alcohol or acetone, something that evaporates quickly, has good solvent capabilities. Use a lint-free soft cloth or a Q-tip, cotton bud, as some people call it, and just very carefully clean it. I try to use a circular motion, working out from the center to the outside, and make sure that there's no streaks, anything left on it. I mean, it should be perfectly spotless when you put it back in the machine. The other part of care of your machine is alignment. So if you look at a perfectly aligned machine, you get your CO2 laser tube, it's shooting its out, hits a 45-degree mirror, goes through your optional beam combiner, hits your other 45-degree mirror, bounces over to the print head, hits its 45-degree mirror, and goes straight down to your surface. Now, this is in a perfect world. What happens when you are misaligned? So here's a misaligned laser. Now, if I take, and you see this beam is coming in and it's hitting roughly in the center of this mirror, but as this carriage moves away, you'll see that that beam progressively gets off. Now this is greatly exaggerated just to show the point, but you can see that that beam is going way off the mirror in the end, and if your carriage is at its furthest point, you're not going to have anything going to your work surface. Even if it's moving just a little bit, it can cause your beam to not travel where it should. So you can end up with not perfectly straight lines or dimensions that are slightly shifting over the period of your work. Same thing with the second mirror. If it's not aligned, as your print head moves away, that beam starts traveling off. It's no longer hitting the center of your lens. It's no longer hitting where it should on your workpiece. So why would you, when do you align the mirrors? Well, right after you get it, for starters, because they're not going to come aligned. Even if they did align them at the factory, they're going to get bounced around in shipping, and the UPS guy is going to drop a kick it a few times on his way up to your door. So be careful, or not be careful, but be diligent right off the bat. Align your mirrors. What's the process? So for starters, you would, and I'm not going to go through and demonstrate this, I'll just give a quick description. You would start with your carriage as close as possible to the front, and you're aligning this mirror. So you would put a piece of paper or tape or something over this second mirror, and then turn your power way down on the laser tube and hit a quick test, and it'll put a dot on that piece of paper, and then you move it back. You move this carriage all the way back as far as it will go. And then once it's back, you press another test shot. And then if that dot shot does not hit in the same spot, you adjust the adjustments on this mirror to move the beam into alignment. So if you look at a mirror mount, you'll see you've got these 3 adjusting screws and some springs. So you loosen these jam nuts and twist these thumb screws to adjust. Now this is a carriage mirror. The mirror in the back here is mounted the same way, so the process looks the same. So once that's aligned, I like to put the carriage at the middle point, and this is just for ease of working on things, getting to things. Then you'll do the same thing with this mirror. You'll put a piece of paper in front of this hole on the print head, and then move the print head as close as possible, shoot a test shot, move it as far away as possible, shoot another test shot, adjust your mirror to bring those in. Rinse, lather, repeat until your dots hit in the same spot over and over. It's more important that they hit in the same spot than dead in the center. If you'd like to see demonstrations of mirrors, there's lots of people that have done these demonstrations. If you're interested in me setting one up, let me know in the comments. I will set up a demonstration. So if you ever need to remove and replace these mirrors, if they've been damaged, you're cleaning them, whatever, this little piece here is just threaded on. You just unscrew that cap, take the mirror out. Again, make sure you're wearing gloves, clean your mirror or replace your mirror, screw it back on, and you're good to go. The print head mirror is a little bit different. So if you look at a diagram of the print head, you've got basically it's a big aluminum cylinder, and on top the mirror is mounted with this screw and this mirror retaining clip. And you just loosen this screw, pull that and the retaining clip off, and the mirror, just lift it off, and you'll be able to clean it, put it back together. So you see this physical retaining clip and that screw. The other piece of for cleaning and care is your lens. Again, this print head, at the bottom there's a lens retainer cap. You'll unscrew that, and the lens will be in there. You'll pull it out. Again, gloves, isopropyl alcohol, very carefully, clean it, lint-free cloth, make sure it's spotless. Again, make sure you get it oriented the right way when you put it back in. If you got a plano convex lens, which is most likely, look at it. If the image is distorted and shrunk down, that's the convex side. If you're looking at your reflection and it's, you know, a clear full-size reflection, that's the plane side. Plane side should always go towards your workpiece. Okay, well that covers all of the pieces of the light path fundamentals that I wanted to cover. If you have any more questions or you want me to cover something in more detail, let me know in the comments below. If you would like me to cover the CO2 laser tube, I can try and put together a video on that. I plan to do some more upgrade videos in the near future. I've got several upgrades I'd like to do, demonstrating why I need to do them and what their purpose is. And with that, I hope to hear from you guys again, and see you next time.